So we're going to go ahead and take a step forward from multiple regression to logistic regression. So logistic regression is basically a multiple regression where we've changed one aspect of the model. And that is that instead of a near infinite number of predictors predicting one continuous variable, we now have the same model, same predictors, however complex we want to get, however many levels we want to get, but the outcome is no longer continuous. It is a dichotomous categorical variable. So logistic regression really is when we're wanting to predict group membership. And group membership can mean lots of things. A lot of times it's a diagnostic question. It's a hire or don't hire. It's a needs help, doesn't need help. Gets into a advanced group or does not get into an advanced group. That's really what we're looking at. We're using this to, instead of just predict a continuous variable, we're now trying to predict group membership. We're going to talk about what logistic regression is. We're going to talk about the various ways that we go through with logistic regression and the effect sizes. And finally, we're going to talk about a type of logistic regression, ordinal logistic regression. And I want you just to keep in mind that we're mainly going to focus on the differences between this and multiple regression because it's effectively the same technique and it has a lot of the same assumptions and a lot of the same processes. It's simply that the outcome is no longer continuous. So if we're analyzing a categorical dependent variable, linear multiple regression is not appropriate for categorical DV. First, one of the assumptions of regular multiple regression is violated, the normality or linearity of the actual outcome. Also, even if we did run it through, it would often underestimate the relationship. So I have an example here of where we're trying to draw a linear relationship between a categorical variable, 0 or 1, the presence or not presence. Now notice that in the presence, there is higher scores, generally, of whatever's being measured. In this case, it looks like INAT, we'll call it initiative. Really doesn't matter. But again, there is a difference here. But because a regular multiple regression is trying to treat that outcome, which is a dichotomous categorical outcome, as a continuous variable, it's going to underestimate that relationship. How much can we predict whether you are or are not in a group based on your score in initiative in this case? Because what's actually happening here more visually is something like this. And what we're trying to do is use continuous predictors, so basically our IVs, to predict group membership. And what we're wanting to do is where is, instead of a linear line, where is the cutoff point where we have the least error? At what point in the relationship between our predictors, our independent variables, our continuous variables, our regular predictors, just like in multiple regression, are indicating whether or not you should be in group 1 or group 2. So it's a different question. We're no longer looking for a linear relationship. We're looking for the optimal solution to how often then are we correct if we use these predictors to say you're in group 1 over group 2, or group 1 versus group 0, whatever you label them. A lot of times it's accept, not accept, needs help, not needs help. And again, this is often going to be used in more practical settings. So when are we going to use logistic regression? When our outcome variable is categorical and dichotomous. Basically, we are trying to sort people into two different conditions, two different groups, two different probabilities. Our predictor variables can be pretty much anything with multiple regression. They can be continuous, they can be categorical. If they're categorical, we'll have to dummy code them. If they're dichotomous, we can simply put them in. And like multiple regression, it examines the strength and direction of each relationship, so each independent variable on the prediction. It makes predictions, and again, we can go as complex as we want, just like multiple regression, and it's the same technique. We can create interaction terms, we can create nonlinear terms, we can use dummy codes, and we can also create models that include various predictors or do not include multiple predictors. Unlike multiple regression, logistic regression purpose is not to look for a linear relationship, but to classify units and to then measure the accuracy of that classification. How much can you trust this particular model with these particular predictors to tell you whether someone should or should not be in a particular group or category? There are some other ways to look at this. We will be discussing discriminant function analysis that is a very specific type of looking at, again, categorical variables, but it usually works better with multiple actual outcomes. In other words, a categorical variable with multiple levels. Also, the assumptions of discriminant function analysis are different than the assumptions of logistic regression. We'll also at least touch on multi-wave frequency analysis. I want you to at least know what this term is. A multi-wave frequency analysis is when all of your variables are categorical. In other words, you have no continuous predictors whatsoever. All of your IVs are categorical and your DV is categorical. In that case, we'd actually be using a multi-wave frequency analysis. That doesn't come up that much, and we're not going to go into detail on that one, but I do at least want you to know what it is and when would you use it. So our example for our introduction to logistic regression is going to be, we want to examine the relationship between smoking cessation. So our categorical DV, our outcome is whether or not someone stopped smoking. That's a yes or no. They either have stopped smoking or they haven't. And we want to predict whether or not you would be someone who had stopped smoking by the treatment type, your number of years smoking, and your parents' history of smoking. So in other words, we have 3 IVs that are continuous, and we're going to ask the question, can we use these 3 IVs to find out if someone would be more likely or less likely to stop smoking? So let's start talking about the statistics used. Now again, I really want to stress that the technique is the same, but what we're reporting and what we're looking at is somewhat different because we're no longer looking for linear relationships. We're actually looking for accuracy of prediction, accuracy of categorization, which is a yes or no. So we're generally going to be using chi-squares, which is a method that is a non-parametric statistic that looks at categorical trends. It's looking for the discrepancy between expected frequency and observed frequencies. In other words, how often when we predict someone being in one group or another, are they actually in that group? Are they properly classified or misclassified? And again, when we're creating the initial model, we'll have that information. We'll know whether they smoked or not, or stopped smoking, or whether they're still smoking. The question is based on our model, would we have predicted them to be in that category? And the chi-square is then going to look at our prediction versus the reality. So how we determine if a particular IV is a significant predictor is a walled chi-square. So for example, is the number of years smoking a significant predictor of whether or not someone would stop? So we're looking at just that individual IV in this case. And walled is basically the B weight of the predictor divided by the standard error or standard estimate of the error of the B weight. And again, this will be provided for you when we actually run this statistical analysis in SPSS. So we use walled chi-square to look at each individual predictor, but we also need to look at the whole model. And for the model, we are using, and this is probably one of the worst names in statistics, the -2 log likelihood. The main reason this is such a horrible name is that one of the things we need to do with the -2 log likelihood is subtract it from something later on in an equation I'm going to get to. So just be aware that that first negative is not a minus, it's a part of the name, -2 log likelihood. So the -2 log likelihood functions the same as any omnibus test that is simply looking at model fit. It's an estimate of model fit. How well does the model predict the outcome or group membership? So how well does the combination of treatment type, years of smoking, and parents' history of smoking on whether someone is likely to stop smoking or not? How accurate is that estimate? And how close are the predicted outcomes of smoking or not smoking to the actual smoking cessation rates that we have in our data set? Generally speaking, with the -2 log likelihood, the smaller the number, the better. So, with -2 log likelihood, does the log likelihood decrease or increase significantly with the addition or deletion of predictors? So again, much like with multiple regression, as we look at multiple models, as we add additional predictors, we want to ask, does each additional predictor add to our accuracy? So can I improve the model by adding parents' history as an additional variable? And the way that we would look at this is we would actually look at, again, we run a chi-square comparing the -2 log likelihood of the smaller model subtracted from the -2 log likelihood of the larger model. the difference between the model with and without the addition of that new variable. So again, if we're wanting to compare two models, we're looking at a delta, a change in the model's strength. The strength being measured by -2 log likelihood. And the way we calculate that is we'd actually take the -2 log likelihood of the smaller model, the model with less predictors, minus the -2 log likelihood of the larger model with more predictors. So the difference between the model with and without the addition of parents' history. The degrees of freedom for that chi-square test, delta change, is the degree of freedom for the bigger model minus the degree of freedom for the smaller model. And then we just take a look at the at the chi-square table. Also, again, SPSS is going to give us whether or not that was a significant change as we move on models. But again, what we're looking at is the -2 log likelihoods.